Good morning, everyone. We are from Group 5, and today we are proud to present our final project for network analysis and design. Our selected organisation is Majlis Bandaraya Melaka Bersejarah, commonly known as MBMB. Our team members are Ami Haris, Suhaidi, Naim Zakwan, Adam Hakimi, Iqbal, Tanisha, and Tanutra. Let's start with a brief introduction. MBMB is the municipal local authority responsible for urban administration in Melaka. Their main headquarters in Graha Makmur, and they also manage 7 branch offices. Their core business rely heavily on digital system for city governance, specifically their critical revenue collection system known as Sistem Kutipan. It's a massive operation supporting around 1,200 staff at HQ alone and managing over through 1,050 hundred and nodes.
However, their current network faces several critical problems. They suffer from several network congestion during peak hours due to an unsegmented flat network architecture, critical data, silos without inter-department traffic management, and zero wide area network failover capability, creating single point of failure for MBMB system Kutipan revenue system. Our project scope focus on completely redesigning the MBMB HQ network infrastructure and the one edge connectivity. This covers all 7 branch office across Melaka. Our main objective are to analyze existing traffic flow to identify bottlenecks, design a fault-tolerant Cisco 3-tier hierarchical architecture, and prioritize critical application through structured QS implementation.
Moving to our logical design, we are shifting MBMB from a fragmented, flat network to a structured Cisco 3-tier hierarchical model, which includes core, distribution, and access layers. This eliminates broadcast congestion and unsegmented data silos. Through our 2-part flow spec calculation, analyzing aggregate traffic demand and peak hour utilization for 1,500 plus end nodes, we determine the network requires a 2 gigabit per second composite backbone to reliably support MBMB HQ and the 7 branch 1 links. For technology choice, 10 gigabit Ethernet was selected for core interconnects, providing a 60% safety margin above the 2 gigabit per second requirement. This ensures low latency for the critical system Kutipan revenue system and supports future scalability.
Good evening, I'm Tanutra Dr. Balaraman and today I'll be presenting about logical design details. Diving deeper into the logical design details, for interconnection, we utilize OSPF for dynamic routing and rapid convergence across VLANs, hot standby router protocol for gateway failover and high availability, and Ether channel for link aggregation to provide redundancy and increased bandwidth. For network management, we implemented a centralized in-band management system via a dedicated isolated VLAN for secure administration. We use SNMP v2 for real-time network performance monitoring and a syslog server for centralized event logging. For security, we deploy next-generation firewall to protect the network perimeter from external threats, inter-VLAN access control lists to enforce traffic segmentation policies, and IEE 802.1x network access control for port-based authentication. Thank you.
I'm Tanisha Lichumanan and I'll be presenting about the physical design. First, let's look at the current versus future infrastructure. Currently, the network uses an ad hoc and unstructured cabling system, which can cause maintenance difficulties and reduce reliability. In our proposed design, we will implement a fully structured IT data center environment. This includes adding a UPS or uninterruptible power supply to ensure continuous operations during power outages, as well as precision cooling system to protect the hardware and maintain optimal performance for MBMB operations. Next is the wiring scheme. We choose a centralized hierarchical star topology because it provides better network performance, simplifies fault isolation and troubleshooting, and reduces maintenance overhead. This design connects Graha Makmo headquarters with all 7 branches offices in a more efficient and manageable way. Finally, for the cabling standards, we use fiber optic cables for the backbone connections between the distribution and core layers, supporting speed up to 8 to 10 gigabits per second. For end users devices, we use category 6 UTP cables which support 1 gigabit per second and power over Ethernet or PoE, allowing desktop computers and Wi-Fi 6 access points receive both data and power through a single cable. Overall, this physical design provides a faster, more reliable, and scalable network that supports the organization's current future operational need. So that's it from me. Thank you.
Now, let's go over our addressing and routing strategy. We are using a private class C schema, assigning a dedicated 192.168 subnet to each department VLAN. For daily operations, standard endpoint devices will connect automatically using DHCP. Meanwhile, our servers and core network infrastructure are assigned static IP addresses to ensure they remain consistently accessible and easy to manage. For internal routing, we selected OSPF as our interior gateway protocol. OSPF provides rapid convergence, which means it quickly adapts to any network changes. This ensures that our traffic routing remains highly efficient and reliable across all VLANs and branch VPN tunnels. And finally, for external routing, we deploy BGP v4 at the one edge. BGP actively manage the best path between our dual internet services providers. This setup provides strong redundancy and automatic failover, guaranteeing that our outbound internet and inter-branch traffic stay online without any disruption.
To conclude, did we achieve our objective? Yes, we successfully achieved all project objectives. We resolved broadcast congestion and secure the network perimeter, implemented a Cisco 3-tier redundant architecture and guaranteed 100% reliability for MBMB critical system kutipan revenue system. Thank you.